Specifically, we've got a grand total of, find my cursor so I can highlight where we're at. We've got a grand total of 8 computer science books. We've got a grand total of 5 French books. Don't know what they are. We're going to assume they're different copies, not duplicated copies of the same book. And what we want to do is we would like to display 6 of those books on a bookshelf. Okay? Now, the assumption here is that you don't do crazy things. You actually put them on the shelf like what you would normally see at a library or a bookstore. Maybe at your own personal place too, as long as you're not doing something crazy like what my husband does and puts the spine towards the wall every so often. We're assuming that the actual spine of the book points out. We're assuming that the book is right side up and not upside down. Why? Because if you have those extra options, the actual count gets higher because you have more options. Okay? So we're assuming here that the books are we're only looking at the order of which the books are placed, not the orientation of whether the books are upside down or right side up. Okay? So we want to display 6 out of those, 13 books. Okay? So you decide that in picking those 6 books to display, you're going to pick 4 of the computer science books, and you want to select 2 of the French books. And what we want to do is how many different ways are possible to display these books, or really to put these books on the bookshelf, if you actually group the books of the same subject together. Okay? So if we look at this similar to what we've done yesterday, what did we do? We had this sort of placeholder idea. So we have 1, 2, 3, 4, 5, 6 books. Now, what would you need to decide first before we go any further figuring out how many books to put where? What's something you'd have to figure out? Specifically thinking with that very first book. What would you need to decide there? Well, for sure, you definitely need to figure out what book you're going to put first. I'm thinking slightly more specific than that, although it might be what you were thinking. We've got what in terms of books? We've got a grand total of 8 plus 5, so what is that? 13 different books we could select from, but we're given an extra criteria that we need to put all the computer science books and the French books together. Exactly. So we need to figure out if we're going to be using a computer science book or a French book first. So what do you guys want to do? Do you want to put the computer science books first or the French books first? Sure. So for this one here, in terms of our computer science books, I'll do C for computer. So we'll have 1, 2, 3, 4 computer books, and then we would have 2 French books. Okay? And I'll put a little line here. This is pretty common when people put like a line to indicate that you've got a division there. It doesn't actually mean divide. It just means it's just an easy way in your Scratch work to say, hey, we've got, these are one type of object and these are a second type of object. So if we start looking now specifically at the computer science books, how many possibilities do we have to select the first computer science book? Don't overthink it. I think you're looking at the wrong number. Yes. So we've got a grand total of 8 computer science books, 5 French books, and in terms of the ones we're displaying the 2 and the 4. So we already took care of the 2 and the 4, so now we're just focusing on the 8 computer science books that we're going to pull from and 5 French books that we'll pull from. Now, in terms of the next book, do we still have 8 options for our next computer science book? Nope. So what number should I put next? Yep. And what about for the next 2 slots, which are the remaining computer books? You got it. So this is going to be 8 times 7 times 6 times 5, and that takes care of your computer science books. Notice, just like what we talked about in some of the examples that we did together last time, this is a situation where once you put that book on the shelf, you can't use it a second time because it's already been used. So this is one of the situations where you're not allowed to repeat objects because once you've used it, that's it. It's been used. Okay. Now, that takes care of the computer science books. Then we jump over to our French books. What happens on these two slots? What number should I insert right there? Yep. So there's a grand total of 5 French books. So the first one, in terms of your French books, you could pick any of the 5. And then because you've already selected 1, you then have 4. And so you then multiply all these guys together and get a number. And I am now definitely regretting not have multiplying those numbers together for us ahead of time. I did somewhere, but as I'm looking around, I don't see that piece of paper where I wrote out that number previously. Okay, so this would be where you would multiply all of these guys together. It'd be 8 times 7 times 6 times 5, and then times 5 times 4. So we've got 20 times some other number. Okay. Now, is this guy, whatever number it actually turns out to be, is that the final answer for this question? What do you guys think? Ooh, excellent. We have 1 vote for yes and 1 vote for no. One of you is correct. So what do the rest of you guys think? So if you think the answer is yes, it's kind of hard to explain. But if you think the answer is no, what would be another way or another option of how you could put the books on the shelves? And that right there is how you can determine if there's more options or not. So what do you think? Is there another way to put 6 computer science and French books up on a shelf than what we just did right here? You got it. So there is a second case. And the second case, you still have to group the French books and the computer science books together, but you totally could have put the French books first and the computer science books second. So this is a situation where we actually have 2 cases. So in this second case, notice in terms of what we would do, the French books would be first, computer science books would be second. You would still get the exact same numbers. So you'd still have the 5 times the 4 for the French books. You'd still have the 8 times the 7 times the 6 times the 5 for the computer science books. And I totally sneakily, while we were talking, grabbed a calculator and multiplied those numbers together because I did not want to do it all that in my head, especially while I was talking. And this number turned out to be, when you multiplied it together, 33,600. Now, here's the big question of the day. What's the actual answer? Those being the only 2 cases we do actually have here. So what would we do with those 2 pieces of information, those 2 different cases? In other words, those 2 answers previously of 33600. You got it. You would simply add the 2 numbers together. They're 2 separate cases. You don't have a situation where you have any overlap between those numbers where you counted up the different ways of putting the French and the computer science books together on a shelf. So our answer here is totally going to be the sum. So that, let me put in the middle work here, so if you're looking back at this in the future, you know what happened. So you add those 2 cases together, and that would be 67200, which is exactly what you guys sent in. Okay? So this is an example of different cases, and that's actually one of the reasons why I put this question on there for you guys to look at previously, was because it was a little bit different. You had to worry about the 2 different cases. The question above this question, too, that dealt with the area codes, for that one you actually could write it as 2 different cases, or you could write it together. There was a couple different ways to do that one. So I'll post a solution for that one for you guys. All right. So any questions on that number 3, or does that make more sense? All right, I'm not seeing any questions come in, although if you do have them, definitely shout them out, and we'll come back to it. But we did have one last question here that dealt with this question number 4 that talks about putting people in a circle. Now, when you put people in a circle, it is similar to what we have been doing, but a little bit different. All of the other questions that were before question 4 and all of the other questions that we talked about all together, I probably shouldn't have said all together, that we've talked about when we were together, we're all dealing with if you were putting people in essentially a line. You're putting people in a row. I shouldn't say people all the time. Objects in a row, objects in a line. Bookshelf, they were in a row on the bookshelf. So it was always some sort of ordering. There was a first person, there was a second person, there was a third person. And yes, I'm totally accidentally went back to people just because this question number 4 deals with people. Okay. Now, what's different about this question number 4? This question number 4 is dealing with now a circle. What's different about a circle as opposed to a straight line? Here's your straight line. Here's your circle. Well, with a straight line, you have a very clear starting point and ending point, or if you prefer in this orientation, right and left, you've got ends. In a circle, you don't. It's all the way around, okay? So here's the big thing in terms of the difference. Typically, in how you see these questions worded, it's often things like people are seated around a table. But in reality, it's almost better to think about it when you're first dealing with these type of questions. It's like, remember the childhood game of like Ring Around the Rosie? People like held hands and went around in a circle and you spun. That sort of movement of spinning around is perhaps a better way of thinking about it when you're first starting. Why? Because it gives you that there's no clear start and end. The only thing you care about is who's on your right and who's on your left. So that's the sort of orientation. Now let's apply that here. So in terms of a picture, what people will often do is put these little placeholders right here. So notice these little lines was my trying to represent the same little placeholders that we've had before, but now it's in a circle. Musical chairs, that would also be a good idea, where it's before everybody tries to get the chair. It's while you're still walking around plotting perhaps the chair you want. Okay. So here we've got our 4 slots, we've got our 4 people. So what happens? Person A, fill in the appropriate name that you want for person A. Maybe that person sits in this first chair. Okay. Now, I don't know who person A is, but if we think about this in terms of all the possible people, I arbitrarily picked this slot here that's sort of upper right-hand corner. How many different people could potentially sit right there? Don't overthink it. How many total people are we currently dealing with? You got it. So any of the 4 people could sit there, okay? So this is like the first person who came into the room and sat at the table, okay? So then if you look, and I'm going to go ahead and just go clockwise around, but you don't have to. You could go the other way around too. That's totally fine. So maybe the next person comes into the room, and they sit here. How many possibilities or how many different people could potentially sit next to that first person? Again, don't overthink it. 3, because you've already, one of the 4 people have sat down. So yep, you guys are right. All of you who sent in the 3s. Now, what do you guys think? If we keep going around, how many people could potentially sit in this next chair based on the work we have so far? Again, don't overthink it. Remember, there was a total of 4 people, and so far 2 people have already sat down. You guys got it. So this would be, there's 2 potential possibilities for the next person walking into the room and sitting down at that chair on the table. Now, last seat left, how many possible people could sit there after we already have the other 3 people? And you got it right. Now, right now with what we have, this is 4 times 3 times 2 times 1, which, as we saw last time, is totally exactly the same as 4 factorial, okay? Which is the 4 times 3 times 2 times 1, and we'll go ahead and put the answer there at the end, okay? Now, if this was a line, a straight line, or even, I guess, a curvy line, as long as it was sort of in a row, in an order, maybe it's them, I don't know, dancing in a line, whatever it is that they're doing. If it was in a line, we'd be done, but we're in a circle. So in a circle, the only orientation that you care about is actually who's to your right and who's to your left. So what does that mean? If the 4 people were originally seated at chair 1, chair 2, chair 3, chair 4, what happens if everybody stood up and moved over 1 chair to the left? Well, it's the exact same circle. They're just sitting 1 chair to the left, and in terms of counting of people in a circle, that's actually considered the same circle, I guess. I was trying to think of a different word than circle, but that's considered the same thing. It's considered still in that same count. Okay? So if all these guys, so musical chairs was actually a really good thought in terms of this with the table. So if everybody stood up and moved 1 chair to, let's make sure I'm in the right orientation if I go this way on you guys, 1 chair to the left, well, they could have been in their original chair. Then they have the 1 chair to the left that they could have been in. So if this is the original chair that dude was in, and then he goes 1 chair to the left, well, they could do it again. They could stand up and go 1 chair to the left again, and everybody would stand up and go 1 chair to the left. Well, then the original guy could be over here with this new spot that's, in terms of 4 chairs, exactly across the table of where he originally was. And then maybe they do it another time. They all stand up, they move 1 chair to the left, and then the original guy that's where that number 4 was, he could end up in that last little dotted location right there. Okay? Now, if they all stand up and move 1 chair to the left again, what happens? They go back to the original marked chairs. Okay? So, any guesses why I would have done that whole little expose right there? Because remember, in terms of the count that we care about with circles, whether those guys stood up and moved over chairs or not, it didn't matter. It's still considered the same orientation in terms of them being in a circle. Any guesses what we're going to do with that 4 right there? Because the assumption here is that we don't have marked chairs. Anybody got a guess? All right, well, I'll give a little bit more background. So the 4 factorial right here assumes all the chairs are marked. So it's like a red chair, a blue chair, a green chair, a yellow chair. And so when the people come in, you know exactly what chair they're in. But in a normal situation, you don't know how the chairs are marked. Okay? So the only orientation you have is who's sitting on your right and who's sitting on your left. So if we want to get it so that the chairs truly are not marked and get rid of this assumption right here with a factorial, what we saw is that there's really 4 different situations where these people could sit in marked chairs, so the chairs stop being marked. We've overcounted by a factor of 4. So what you actually do here is you would divide out by that overcounting of a factor of 4. So this would be your answer. It turns out if you are in a circle orientation, so circle with n people, and we're also going to assume n chairs or n positions. The formula is n factorial. Can I go any above? That's the bottom of the page. Divided by n is the official formula. It does assume that the only orientation you have is look to your right, look to your left, and that's how you figure out your orientation or your circular list. It's a weird way of saying it, but it is actually what's going on. Okay? So hopefully that one's slightly clearer. We're actually not going to deal with those guys too frequently, but they are common enough that you want to see at least one case. For us, most of the time you're going to have some sort of way of distinguishing these guys. So here, if you had like a square table, maybe you'd actually be able to distinguish the head of the table, the foot of the table, and maybe some of the chairs on the side. If these guys were marked chairs, you wouldn't divide by 4 again. The only deal here is if you need to put people in a circle and there's no other distinguishable marks. That's the key thing. Okay. But that takes care of almost all the questions from Activity 6. There were only 2 of them that we skipped out on, and you guys didn't say you had any questions from those guys, from them. Okay. So other questions or sort of make sense a little bit more? All right, so I am not seeing any questions come in from you guys, so let us now go and look at a couple of more examples together, okay? So I've got, I think, 2 or 3 examples that are sort of crossover examples from the stuff that we were doing last time, jumping into the stuff that we're about to transition into, that is transitioning from building lists to building sets. So let me switch over here. It says not the right file. So we'll share that one and then not share the other one. I do this thing where I don't stop sharing before I go and share the new thing, just because if I make it where there's nothing shared, all of my little windows where I can see what you guys are saying completely disappear on me and I have to re-find them. All right, so before we go too much further, let's go ahead and do a summary of the different formulas that we talked about last time, because we embedded those formulas inside of examples. And this is also going to give you the technical terms. So everything we've done so far is what's called order matters, and this is where you're building the list or the string or whatever it is you're building, and if you use the same objects but rearrange the order, you count them as 2 separate lists, okay? So that's everything we've been talking about up to now. Repetition allowed and repetition not allowed were those 2 buzzwords we talked about a little bit ago. The repetition allowed, this is where you have formulas that look like exponents or exponentials. So you've got where you pull your number of objects that you're allowed to use and you're never going to decrease. So this isn't where you get to use up an object and then it doesn't stay in the allowable set of objects that you can use. So here you're looking at exponents a lot. Now, is it only a single exponent for your answer? No, and we've seen that. You could have something like 2 to the 4th times 3 squared, okay? But all your little components would be exponents when repetition is allowed. Okay? Now, with repetition not allowed, this is when you'd use your factorial or your falling factorial. This is where each time you use the object, your set or your number of objects that you're allowed to use for the next position decreases. So this is like with, well, most of the examples we just looked at, but especially I was thinking in my head the one with the books. You put one book on the shelf, you now can't use that book again later on. Okay. So this is the summary of all the formulas. We'll actually have 2 more situations. I'll typically, if we're in a room with a board, write a big sort of 2x2 chart where you've got order matters, repetition allowed, repetition not allowed. And if we get a chance, I'll write that chart for you, but it'll probably be on Monday once we have all the formulas. Okay. So today we're going to look at 2 more formulas depending on time. So that's the stuff we've talked about. So let us look at an example. So suppose you have this example right here, and it says, how many 3-letter words, and this words is the same thing that we did last time, where word is not dictionary words, it's literally strings of characters. In other words, if it's gobbledygook, that's okay. Okay. So we want 3-letter words of distinct letters, so you're not allowed to repeat the letters in these words that you build, and those letters can be formed from the letters of the word angle. So any guesses what we would do here? Don't overthink it. This one was trying to be a easy example at the beginning, mainly because I didn't think we would do as many examples on activity 6 as we did today. So 3 letters would mean we would have 3 positions. And if we wanted to figure out our numbers that we would multiply together, what should we do next? You got it. So this would be exactly 5 times 4 times 3. 5 would be everybody from angle. And then these guys would be where you've already used up a letter. And when you multiply that together, that should be what, 60? That looks like a 60. Okay. Now, the reason that this one is in this particular location is typically this is right after the first time we've talked about the formulas. So if we did this in terms of formulas, this is a falling factorial. You put the 5 inside the parentheses, and you'd put the 3 in that subscript. And this tells you you start with the number 5, and you're going to go out 3 positions. So the 5 here comes from the angle. So here, n equals 5, and this is the number of letters in that word angle. And the K equals 3, that subscript is 3, and this is the number of letters in the word that you're building. Okay. Now, if you don't actually put this symbol in, notice, not that huge of a deal. You can do that the same sort of placeholder scratch work that we've done before we even knew the symbols, and you'd still get the correct answer. But the point of this example was to that interplay between the symbols and the work that we already knew how to do. Okay? But that's it for that example. It was no more complicated than that. Okay? So, next example. Now this next example is a little bit more complicated than the last one. So this next example is, I'm totally picturing in my head an elementary school classroom type thing, okay? So you've got some sort of situation where you've got 10 boys, 10 girls, and what they need to do is they need to stand in some sort of line, and they need to alternate for whatever reason, boy, girl, etc., okay? So if we wanted to figure out how many ways that these guys could do that, any guesses what we would need to do? Well, we could actually approach it the exact same way that we've done in the past. Okay? So we know there's going to be a grand total of 20 of them. I'm not going to write out 20 little placeholder blocks, so we'll put a dot, dot, dot at some point. So we've got first couple guys. I'll go out, oh, how about 4? We should be able to see a pattern by then. And then we'll go ahead and grab maybe the last 4 as well. So that's 8 out of the 20 kids. Okay. So in this case, if we go ahead and look at this very first person, do you want this person to be a boy or a girl? Is there anything in this problem that says it matters? If yes, we need to pick the one that it matters. If no, you guys get to pick which one we want to do. Do you guys got a preference? Ooh, I am going to put a pause on your guess with 20 because that actually is a way to do it, but we'll do that as a way too. So let me tag this so we don't forget about that. And that is actually a very sneaky way of doing this problem. I'm going to put that as a way 2 down here. But correct, in this particular question, the way it's phrased in, let's face it, a relatively sparse wording, there's nothing in that wording that says you have to have a boy first or a girl first, so you get to pick. So because I actually, when I typed this up last night, I wrote down here, cursor, I cannot find you. Because I wrote here, boy, then girl, I'll go ahead and just put it in that same orientation. So if the first kid's a boy, the second one would need to be a girl. The third one then has to go back to the boy because they're supposed to be alternating and so forth. Okay? Again, it didn't matter which way you picked. I just did it in the same order of the little boy-girl slash up in the problem. Now, when you get to the very end, last kid in the row should be what? A boy or a girl? What do you guys think? Right, it should be a girl. And so then when you know who the last kid in the row is, we can go ahead and backtrack this alternating thing. All right. Now, if we go and look at the counts for this first little boy right here, how many possibilities of the kid who's actually standing there? How many possibilities do we have? Yep, we've got 10. Now, when we go over and look at the next position is a girl. How many possibilities are there for the little girl to stand there? Also 10, correct, because there was 10 of each. I realize this is a very contrived example. It's probably very rare that this actually happens. If you go to the next kid in line, how many possibilities are there now for this little boy? Again, I'm totally picturing, like, I don't know, 6-year-olds. Just because I'm sure for the teacher's sanity, they put them in lines all the time. Yep. And now what about for the second little girl? Again, correct also would be 9 options. And because we put dot, dot, dots, you continue this pattern of once the kid stands in line, you then have fewer children to choose from. So for these last 4 blanks, any guesses what we should put in these last 4 blanks? Correct. So we have a grand total of 10 boys and 10 girls. We're totally going to have all 10 of the boys and all 10 of the girls stand in line. So that means when you get down here at the very tail end, when you grab your last boy and your last girl, there's only one option. But for the previous or second to last boy and girl, there's still two possibilities for the kids who are standing in that line. Now, if we put this all together, we can totally write this in terms of a formula. No, I'm not actually going to write out the integer answer for this one right here. Notice what this looks like. You've got 10, although there's two copies of them, times 9, although there's two copies of them, then a bunch of dots that we didn't write the numbers, then 2, although two copies, and 1, although two copies. Any guesses in terms of formulas what we could write after the equals? Don't overthink it. It kind of looks like a what? Yeah, it totally should look like a factorial. Now, the only difference between this guy, what we just wrote here, and an actual factorial is an actual factorial doesn't have the two copies of each of these integers. Don't overthink it. That just means what? There's two factorials intertwined with each other. So one of those 10 factorials would relate to all of the boys, and one of the 10 factorials, if you rearrange the factors here, would relate to all of the girls. And if you didn't want to write that many characters, you could totally say 10 factorial squared, and you do need the parentheses around the factorial just because of that weird exclamation point involved. Okay? Now, question for you. Is that the total number of ways that these 20 kids can line up in a row alternating boys and girls? What do you guys think? Correct. And so just like when we looked at a little bit ago, we had some other options of how we could orient or create these lists. What's the other situation of how these kids can line up? You got it. So case 2 is you do the exact same thing, except you start off with a girl. And maybe if this is in an actual classroom situation, maybe this is something that one day of the week the teacher's like, yep, we're going to start off the line with a boy, and one day of the week we're going to start off the line with a girl. Okay? But in either case, however it actually happens, overarching number of ways for the kids to line up, you've got these two choices. Now, in terms of the numbers, so before we had 10, 10, 9, 9, and then missing pieces that we didn't write down, and we ended with 2, 2, 1, 1, do the numbers change up here in this case too? What do you guys think? I'm going to need a little more space, so. Correct. So these guys are not going to change, although now I need to get back to a pen. Okay. So we'll still have the same 10 possibilities for the first girl, 10 possibilities for the first boy, then 9 possibilities for the second girl and boy, all the way down to our second to last girls and boys have 2 possibilities, and last boy and girl, well, the only one kid that's left. Okay. So then when we multiply these together, notice you'll get the exact same answer. It's going to be 10 factorial times 10 factorial, one of the 10 factorials representing the boys and one of the 10 factorials representing the girls. And even though the order or the specific orientation of the girls and the boys have flip-flopped, in terms of the total number in this second case, it's still exactly the same. So the answer here would be 2 times 10 factorial squared, or I really should say in terms of counting, the proper answer is always whatever the integer is. So if you go ahead and multiply that out, and I'm just going to give you what the integer answer is. The integer answer turns out to be 26 and then a comma, 336 and then a comma, 378 and then a comma, and then 880 and then 3 zeros at the end. So these are the different ways that the kids could actually line up in a straight line. Okay. So a ton, literally. All right. So that was one of the ways you could do it. And I wanted to make sure that we did this way just again to highlight or illustrate the fact that you can have two different cases. But for this particular example, one of you pointed out that you can actually do this where you don't actually divide it up into cases. All right, so going now back to what I had asked us to put on hold a while back. So first kid in the line. How many possibilities are there for the very, very first child in the line? You completely disregard whether you're going to start with a boy or a girl. Correct. You have a grand total of 20. Now, once you choose that child, and assuming you don't have any transgender children that have a different classification, and assuming that we do actually have only two options. We could do this with more than two options. I just didn't end up writing the question like that. Assuming we do have two options and we know that the kid is either a girl or a boy, what do you know then about the second child in the row or in the line? Correct. So this second kid in the line, once you've selected that very first person, you know for sure that the second not 9, almost. You know for sure that this second person is going to be either a girl or a boy, but specifically it's opposite kid 1. We don't know who kid 1 is. If kid 1's a girl, there's still 10 boys we could choose from. If kid 1's a boy, there's still 10 girls we could choose from. Okay? Now, once you get past the first two children, you know if you're in, like when we did this previously, case 1 or case 2, you know if you're dealing with either a boy or a girl. And so everything here is what? The next two kids, I don't know which one's a boy or a girl because I don't know who we actually selected for that first kid, but one of these guys would be a boy and one would be a girl. We've already had one boy and one girl in the line, so what should be the two numbers in these next two slots? Exactly, they should both be 9s. And then it keeps on going. Again, we don't know if it's a boy or a girl in which orientation in these two second to last slots, but we do know that we have 2 boys left and 2 girls left, and depending on how we actually started, and you'd know that once the kid was selected, here you also are doubled up to 2 like before. Anybody got what the last counts for the last 2 slots would be, or the last 2 kids would be? In other words, anybody got the guess on who the last 2 numbers? You guys got it, perfect. Now, if we write out this formula, it is a little bit different from the other ones. Notice this very, very first number right here is a 20. That second number right here is a 10. Well, this 10 we can group with 10 times 9, and in the missing bit there'd be 8, 7, etc., to 1. So we could actually write a 10 factorial right there. And then this guy right here is a 9. So that's the spot we hadn't picked. And then we have 9, 8, 7, etc., 2, and 1. So we could write this as 9 factorial. And the question, of course, is this number the same as the number that we got previously? What do you guys think? Is this multiplication, because we haven't multiplied it out to get the actual integer yet, is this formula going to give us the same integer that the formula did up here in wave 1? What do you guys think? Fair enough. Hopefully, yes, exactly. All right, so I'm going to do a trick here, and I'm going to show you that, yes, it actually does equal the same thing. I'm going to actually factor the 20, okay? So the 20, I'm going to break it up in 2 times 10. And I'm also going to flip-flop the 10 factorial and the 9 factorial. I'm just going to write 9 factorial first and 10 factorial at the end. Now, I underlined the middle 2 factors. Any guesses why I underlined those middle 2 factors? Specifically, I'm going to try to multiply 10 times 9 factorial to get something. Any guesses what 10 times 9 factorial should equal or does equal? Exactly. So remember, 9 factorial is you multiplied all the integers 1 through 9. 10 factorial is multiplying all the integers 1 through 10. So if you multiply a 10 times a 9 factorial, That is, in fact, 10 factorial. And notice what we got, exactly the same thing we had up here, a factor of 2, and then 2 factors of 10 factorial. So this one here is exactly the same as way 1. Now, is it harder to see? Because you got to sort of think in your head, I don't really know which one of these kids is the boy or the girl, but I know exactly one of them is once we figure out the first person list. Yeah, it does take a little bit more abstract thinking to build this sequence, sequence of a bunch of factors, but it is 100% going to get you the exact same answer as just breaking it up into cases. Okay? So that would be 2 different ways to do the exact same problem. Questions kind of make sense, at least a little bit so far. All right, I am not seeing any questions come in, so let us look at the last example I have on this set of slides, and then we'll jump into some more examples. I had just broken them up into 2 different slides, so the file wasn't too big. Made that mistake when I've done one of the files in this class before. All right, so the last example on this slide, and then we'll move on to some other examples that look a little different than these guys. So this example says, we would like to build words. Again, these pseudo words, we're not assuming they're actual dictionary words, so really they're just strings. So we want to build distinguishable words. In other words, if you rearrange the letters of this word Mississippi to build the word. So what does this mean? This means, since it doesn't tell you how long the word is, the underlying assumption here is that you are going to use all of the letters from the word Mississippi. You want to rearrange them. Okay? So if you prefer, you permute them to form new strings of words or new strings of letters. And the key thing here is also this buzzword of distinguishable. In other words, if you rearrange things and you get the exact same string of letters, don't count them twice. Okay? So there's a couple things that we need to know ahead of time. And one of the things that we need to know ahead of time is how many total letters are in this word. So did anybody happen to count up how many letters were in the word Mississippi? Yep. So we have a total number of letters of 11, but what's different about this word than the couple of other times that we've built words, both today and yesterday? You guys notice anything that's pretty fundamentally different about this particular word? You got it. We've got repeated letters, and that's actually going to be a huge factor in this question. Now, in terms of this word, we've got what? We've got an M. There's only one M. We've got an I. How many I's are there? Have you guys spotted how many I's? I think those are the only different words in here. 4 I's. Yep, that's how many I spot. How about S's? How many S's did you guys spot? I'm only seeing 2 P's. Yep, I see 4 S's as well. All right, so this over here to the side is the key things that we're going to be dealing with. Now, here's the other key thing. If we just rearranged all of these letters, what would happen? There's a grand total of 11 letters, so if we permute them or if we rearrange them to get new words, there would be a grand total of 11 factorial new words. Okay. Now here's the problem with if you have more than one copy of your letter in your word. Okay. So I'm going to go ahead and label something. So suppose we rearrange these guys and we got M, maybe M didn't move. Then maybe we got S, 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 then maybe we got I, then maybe we got P, I, P, I, S. Make sure I got them all. 4 S's, yep, 2 P's, yep, 4 I's. All right, we're good. Now I'm going to put subscripts on these guys to distinguish the letter I, the 4 I's from each other, the 4 S's from each other, and the 2 P's from each other. So with respect to S's, there's 1, 2, 3, 4 of them. With respect to I's, there's 1, 2, 3, 4 of them. Wow, I can't do the numbers right. 1, 2, 3, 4. And with P's, there's 1 and 2 of them. And I didn't bother with a subscript on the M because there's only one of them. Now, the 11 factorial up here, if you rearrange these letters, it'll give you another number in the count. Okay? So I'm going to rearrange these guys. So M, S, 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 I, P, I, P, I, S. And the M, again, no subscript, but the S's, 1, 3, 2. The I's, 2, 1, 3, 4. The P's, 2, 1. The S, 4. That is considered a different word inside of the 11 factorial. Now look at those two words closely, those rearrangements of the letters of Mississippi. Does it actually look like it's two distinguishable words? Should those two guys be counted as two different words in this situation? What do you guys think? Should they be counted as two different words, or should they be counted as the same word? Well, if I hadn't put on the subscripts, would you have thought that they were the same word? Yeah. So these guys turn out that they should be counted as the same word. Should is the key word there, because I should have written all of those letters in the same order. But they're not counted as the same word because of, right now, the subscripts. So one of the things that the factorial does is it is assuming here that each copy of your object, whatever it is actually distinguishable. You could tell the difference between the first S and the second S. You could tell the difference between the first P and the second P. Now, if you actually don't want that to happen, if you actually have four letters S's here are indistinguishable from each other when you actually write them out, that means we've overcounted. We've actually overcounted by a lot. So let's focus in on the easiest one. If you focus in on the P's here, what happens? Well, this 11 factorial will count these two words as two different words if you have P1 first, P2 second, or if you flip-flop it of P2 first and P1 second. Well, that means there's exactly double the number in 11 factorial that you need. Why? Because you counted the same word twice because of that flip-flopping of the P1, P2. Does that make sense? Kind of, maybe? I'm going to write that over here to the side. So with respect to P, so here's our overcounting. Overcounted. With respect to P, we overcounted by a factor of 2. And I'm going to go ahead and actually write it as 2 factorial, and we'll see why here in just a second. Okay? Now, that's with respect to P. If you've overcounted by something, you always divide out by how much you've overcounted. So what we're going to do is we're going to divide out our 11 factorial by that copy of 2. And I actually wrote it as a 2 factorial, and again, we'll see why the 2 factorial in just a second. Now, if we go back and we look at some of these other letters, maybe we go back strategically from top to bottom. The M, there's only one copy of M, so there's no overcounting here whatsoever. It already is unique. Okay. If we look at the I, though, what do you guys think? Would we have overcounted with respect to the letter I? And let me attempt to highlight the I just because it's a little bit harder to see. I. And what do you guys think? Have we overcounted with respect to the I? And remember, I put on the subscripts, but that's a force thing. That's a thing just to illustrate what's going on behind the scenes with the 11 factorial. Subscripts aren't really there in real life. Right, so we're going to have been overcounting with respect to the I's as well. There's a grand total of 4 I's. As soon as you have an I in those 4 designated positions, it doesn't matter whether you put I2 first or I1 first or I3 first. As long as you have I's in all 4 of those positions, it's supposed to only be counted once. Now, notice what's going on with these I's. If you've got your position, if these are the I positions, wherever those positions actually live in your word, what happens? You could have picked any of the 4 not different I's and put them in the first location. You could have put any of the remaining 3 not different i's in the second position. You could have put any of the 2 remaining not different i's in the third position, and then the last I goes in the last i's position. How many ways are we rearranging our i's that really are indistinguishable with each other? In other words, what do those numbers actually represent? Or what should those numbers equal there at the bottom? Hopefully you are all thinking to yourself, 4 times 3 times 2 times 1. Wasn't looking for anything more difficult than that. I'm just going to write it as a 4 factorial because I'm lazy. Okay? So what this is attempting to show is that in terms of the i's, once you get a word, a distinguishable word together, the 11 factorial actually overcounts it by a factor of 4 factorial. So it all looks like the same word if you actually wrote it out without the subscripts. But the 11 factorial is scrambling these little subscripts on the i's. Now, we're not actually going to have any of those subscripts on the i's at the end of the day, so we need to stop overcounting by having 24 different copies of literally the same word. Okay? So here, in terms of our overcounting for I, you'll have 24 or 4 factorial. So 4 factorial factors of overcounting per word with respect to the I. Now, I'm going to throw it to you guys. If we look at the S's, are we overcounting with respect to the S's? And if so, by how much? What do you guys think? Exactly. So the S's would mimic exactly what was going on with the I's. Again, as soon as you have that extra copy, as soon as you have 2 or more copies of the same letter, you're going to be overcounting, and you divide out by blank factorial, and that blank would be the number of duplicated letters. So with S, you have 4 S's, so that means this 11 factorial is overcounting by a factor of 4 factorial, or every time you have a unique word, there's 24 copies of the exact same word with respect to the S's. Now, to get rid of that overcounting, you divide. So here's what happens in terms of our actual answer. You start off with the 11 factorial because that gives you all the different words plus a whole bunch of them that are indistinguishable with each other. To get it back to just the distinguishable words, you divide out by the extra copies of I. You divide out by the extra copies of S, and you divide out by the extra copies of P, and notice the number in front of the factorial is exactly the same as the number of how many copies of the letter you have. And if you wanted to deal with the M2, you totally could, but if you put over here the thing that goes along with the M, that would be 1 factorial, and 1 factorial equals 1. So whether you put that one in or not, it doesn't matter. So the final answer, if you actually calculate that guy, and I'll just give you the integer answer, turns out to be 34,650, which is a whole lot smaller than 11 factorial. Questions make sense? A little bit okay. Okay. I don't see any questions come in from you guys, so let us see if we can't take this information and apply it in another situation. And this should be, yep, that is my last one on that one, so I need to go and grab my other file. All right, so this is the next example, and the examples in this section, we've been dealing with examples sort of in this section for a little while, but the next couple of examples are going to look a little bit different than what we've done before. Okay, similar, very similar, but there's some quirks, and also I just picked some different objects that we're dealing with. So this one here starts off and says, hey, suppose you're playing cards. Suppose you have a standard deck of 52 total cards, and you deal out 5 cards to somebody. Okay? So the question is, how many ways are there to deal those 5 cards or a 5-card hand from a standard deck of cards where you have 52 cards? Okay? Notice here, it doesn't tell you what game you're playing. It doesn't tell you anything that you need to know about what the cards look like. All it's looking at is somebody received 5 cards, and you start off with a grand total of 52 cards. So any guesses how we would get to having those 5 cards, or how many different ways somebody could get those 5 cards? And it turns out you can do it the same way we've been doing it. So if you're wanting to give somebody 5 cards, you can say, hey, they want 5 cards. There's representing our 5 cards. Ooh, almost. You're close, but it's going to be adjusted a bit. So for the very first card, yes, it could be any of the 52. But remember, these are physical objects. So as soon as the person gets given that first card, in terms of the collection of the 52 cards that you're giving that person, how many possible cards are left to give them for the second card? It would be 51 because you already gave them 1 card, so in your entire deck, you're down a card. So what would that tell you about the third card? For this third card here, how many possibilities are left for you to give that other person their third card? At this point, you've already given the person 2 cards, so how many total cards are left? Yep, 50. And you guys tell me what should be the last 2 numbers. Perfect. Now, if we want to write out what this means in terms of symbols, this is exactly our falling factorial. So this would be 52 falling factorial 5. Remember, the part inside the parentheses means you started with 52. The part in the subscript meant that you selected or you gave out 5 different cards. Now, the key thing here is context. So context here is our repetition not allowed. Now, how do I know that repetition is not allowed? This is because we have physical objects and you're physically giving the person that card. So that physical nature of you moving the object around means you're not going to be able to have the duplicated objects. So this is, you have physical cards that you're dealing with, okay? Now, that would be perfect if order mattered. So this one here assumes that, hey, we have, so example, assuming this is a normal playing card deck, maybe the first card was something like a 4 of diamonds. Maybe the second one was something like a, I don't know, Jack of spades. Ah, I didn't do a spade. Oh no. Ah. There's my horrible spade. It does not look very pretty. We'll stay away from spades. So maybe we have another 10 of diamonds. I can do diamonds. Maybe we have a queen of hearts. And lastly, I don't know, maybe we have an ace. Maybe ace of clubs. Okay. So maybe that's the order in which the person was given the cards. Now, if those are the distinguishable cards, in a 52 deck of cards, a standard deck of cards, all the different cards look different. You've got the 4 suits of hearts, diamonds, spades, clubs. Half of them are black, half of them are red. You also have the numbers 2 through 10, and then the non-numbered cards, Jack, Queen, King, and Ace. Okay? So you have 52 different cards. Now, when you're playing cards, and this doesn't say what game you're playing, but when you're playing cards, what happens? Once you're given the cards, it doesn't matter the order in which you're given the cards. The only thing that matters is which of cards do you have in your hand. And here, if you have 5 cards that were given to you, once those 5 cards were given to you, it doesn't matter if they were given to you the 4 of diamonds first or the 10 of diamonds first. What matters is you have these 5 cards. Now, what we just counted up with respect to the falling factorial would count these 5 cards in that order to be a different hand than what I'm about to write. Where this different hand would be what happens if you have the 10 of diamonds first, Queen of hearts second, 4 of diamonds third, Jack of spades fourth, and Ace of clubs last. So the following factorial would count these two guys as different, but based on what we just said, should those two collection of 5 cards actually be counted as different hands? So these guys need to be counted as the same or different, right? They need to be counted as the same hand, which means we've overcounted. Now, we just talked about a strategy that we can do when we've overcounted something. So anybody have a guess on how we can get rid of overcounting these cards? Anybody got a guess on how we could stop overcounting here? And while you guys are thinking of your guess, I'll go ahead and just rewrite what we have up top down where there's a little bit more space. Remember, overcounting, we're going to divide. So the question, of course, is, what do we divide by? All right, I can't tell if you guys are typing or not sure. Ooh, yes. So let's figure out where that 5 factorial came from. Okay, so it does turn out that you want to divide by 5 factorial, and that 5 factorial comes from these guys. So the 52 times 51 times 50 times 49 times 48, that will give you which cards you care about, but in a specific order. You don't care about the order, so how many different ways are there to rearrange these same 5 cards? Well, if you want to rearrange those same 5 cards, so number of ways to arrange or permute these 5 cards, that's the 5 factorial. Well, that means that our following factorial over here is counting all 5 factorial options or ways to rearrange these guys as a different hand in play. You don't want that. So we say, hey, we overcounted by 5 factorial, so we are going to divide by 5 factorial. Okay? So that right there would be the how you would fix this. So notice the top is that standard falling factorial that we've done in the past. And then to make it so the order does not matter, in other words, it does not matter that you grab that first card first, it just matters which card you get, that's when you do the division. Okay? Make sense? Kind of okay so far. Questions at the current moment in time? I see no questions. Okay, so what we just did here is we actually set ourselves up, to build the formula for this new type of thing. And I believe the formula is on the very next page, but let me go ahead and write down what the formula is right here, and then we'll actually talk about it on our next page, or our next slide. The actual formula here is something called a combination. Our falling factorial is also called a permutation. If you notice the titles on some of the previous sections from yesterday and earlier today, you might have noticed the word permutation that we really didn't talk about too much together, but that's what the falling factorial actually measures. In terms of this situation where we've got the order in which the cards were dealt with didn't matter, these are now called a combination. Again, I don't care if you remember that. That symbol down there looks like a fraction, except there's no fractional line. So this symbol right here. You have to have the parentheses. Just like with the falling factorials, you have to have the parentheses. It's part of the symbol. Here, you have to have the parentheses. The number on top tells you how many objects you start with. The number on the bottom tells you how many objects you want. And you're literally building sets. So what this says is you have a total of 24 cards. You choose 5 of them. In other words, you have 52 objects, and you want to build a set that has 5 objects, or 5 of those 52 objects. in it. Okay? Now, just because I could probably pull it up here real fast. Let me give us what that number equals, and what this number equals in terms of an integer, whether you do it or you write it all out to actually get the number, or whether you started with the formula and went backwards. This answer turns out to be in integer form, 2598960. Let's put in the commas. So over 2 million different possible ways, which is why you see a lot of variation if you play cards. All right, so let's go to our next slide, which gives us the theory. So here's the theory dealing with combinations. First thing is to remind ourselves of sets. We've dealt with the definitions of sets and cardinality for a while. Sets here, the key thing is it's unordered. The order in which you write your objects in the set doesn't matter. And the cardinality is your number of objects in your set. Now, this is exactly the same formulas as what I told you before, except for the last one, which is a way that you can write it in terms of only factorials. So the combination here is n choose k, where n is the total number of objects you have, k is the number of objects you select. And the key thing here is, do I have it fly in? Yep, is the objects, once they're selected, you don't care about your order coming in. Okay, so you're literally building little baby sets here. Now, for art class, I would recommend that probably the best way to figure out what's going on in terms of calculating these n choose k guys is using our following factorial that we've done in the past and dividing out by k factorial from a combinatorial setting or from a combination setting that we're doing in discrete math. This is a way that will get you thinking the right way. However, if you prefer factorials or if you've ever taken a stats class, this formula is exactly what they would do over there. Notice it's the same thing. Why? Because the n factorial over n minus k factorial we talked about last time actually is a way of writing your following factorial in terms of factorials. So it doesn't matter which of these you do, but in terms of thinking process, this one would be the better one. Okay, so that's what I'm going to stick with, but both of these are fine. You can also plug it into your calculator too. Okay. So our goal here is counting sets is a thing behind the scenes. With the permutations or the factorials or the n to the k guys, where the order does matter that we've done in the past, the goal there was we were actually counting lists or sequences. Now we're counting sets. All right, so let us now use this notation. Oh, and this is what we saw last time, our multiplication principle where we multiply things together, and our addition principle where if you have different cases, you add them together. This still applies, okay? So this is just a recall of what we did before. So let's actually look at another real example. So this is why I was really happy that you guys asked the question about the book question that we had from last time, because we have another book question. Now this book question is a little bit different. So this one says, all right, you've got fiction books and nonfiction books. We've got a grand total of 7 fiction books and a grand total of 6 nonfiction books. So let me underline these. 7 fiction, 6 nonfiction, and we would like to select 3 out of our 7 fiction books and 2 out of our 6 nonfiction books, and we want to take them with us wherever we're going. So maybe you throw them into a bag, maybe you throw them into a backpack, maybe you throw them into something, but you throw them into some container and you go. Okay, so that's the idea here. Now, any guesses how we would actually, how we would go about, how we would answer this? In other words, how would we go about figuring out how many different ways that we can grab those 3 fiction and 2 nonfiction books? Anybody got a guess? Well, I'll give us a little bit of a boost here, okay, or a first step. You can do it the same way that we've been doing stuff in the past, okay? I'm going to actually put 2 slots, which is not our normal way that we've done it in the past. And I'm going to put the 1 slot as for our fiction books and 1 slot for our nonfiction books. Anybody got a guess of what we could put in each of those 2 slots? And I realize it might be difficult to write it out. Any? Ooh, close. You could actually do the formula in that way. So if we go ahead and do the formula that way, so I don't think I can move this. Yeah, I can't. All right. We'll come back to that one. So I'm going to put it over here. So if we look at fiction and nonfiction, and you did 7 following factorial 3, and over here 6 following factorial 2, which is a great first guess. We're going to have to adjust it though. Now, what does this tell us? This is exactly the same thing as 7 times 6 times 5. So that gets us 3 books out of 7 books, so that's good. And then we have 6 times 5, so that gives us the 2 books out of 6 books, but I'm going to claim that this is actually overcounted. Anybody have a guess how it's overcounted? Because the assumption there with the following factorials is what? The assumption is that you have put the things in a row, or you've put the books in a line, or you've put the books on a bookshelf. Yes, it counts the order the books are in. So here's where looking back at the question is really helpful. Is there anything about that question that says we need to put those books in a row, or in a line, or in an order? Correct. So since there's nothing in that question that actually says you need to put these books in order, that's one of the reasons why when I was talking it out, I gave you guys extra words. And some of those extra words that I said was throw the books in a bag. Now, if you've ever thrown books in a bag, and I'm assuming that you guys have, sometimes if you got a smallish bag and biggish books, they're going to stay in a specific order. But if you have small books in a big bag, what happens? Maybe they don't stay in order, or if you're just trying to take it in a bag and hold the book somewhere else, does the order matter? And the answer here is no. So we currently have order. How would we get rid of the order? How would we make it where it doesn't matter the order in which you grab your books? And the answer is yes. The first one you would divide by 3 factorial. For those 3 fiction books, get rid of the order. And for the second one, you would divide by 2 factorial. And then we just need to calculate what this integer is. Now, the nice thing about this is, notice 3 factorial. 3 factorial is 3 times 2 times 1. 3 factorial, 3 times 2 times 1, that's 6. And 2 factorial is 2 times 1, or 2. So this means this first section that deals with the fiction books, the 6 and the 3 factorial will cancel, so we'll have 7 times 5, or 35. And this second one right here, well, the 2 doesn't cancel with a 5, but the 2 and the 3 will cancel, so we'll get a 3 times 5, or 3 times 15. And then all we have to do is figure out what 35 times 15 is, and it turns out that that should equal 525. And that is a perfectly legitimate way of calculating this answer. Okay? I want to show you a secondary way of calculating the answer. But that way right there is a 100% legitimate way of doing it, and it actually is almost the same way that we're about to do it. Okay? So here's the other way. In this particular case, key things to watch out for is repetition, not allowed, because you have your physical books, and here order doesn't matter. In other words, it's like you're building a set, or you throw everything into a bag. If you have those 2 criteria of repetition is not allowed, you can't use the same object more than once, and the order in which you place the objects, you're not placing it in a line, you're just dumping it in a bag, this is when you would use your N choose K. So a fast way, if all you care about is the formula, to answer this question is for fiction, you could just say, hey, this is 7 choose 3. Now, what could you say for the nonfiction books? How many ways could you select those or choose those 2 out of 6 nonfiction books? And again, I realize typing that one would be difficult. So let me show you how it's typically typed. That big capital C is how it's typically typed. So anybody have a guess what we could put in that second slot? That is, where is it? Let me get a cursor so you can see it easily. Right here. Anybody got a guess? Don't overthink it. Buzzword here of choose typically means you're going to do a combination. So here, order doesn't matter. So this slot here would simply be 6 choose 2. Now if you then wanted to calculate it, 6 choose 2 is exactly 6 times, so this here, is exactly 6 times 5 divided by 2. And 7 choose 3 is exactly 7 times 6 times 5 divided by 3 factorial. So notice in these two instances what happened. We can actually put in equals here, a 3 factorial on the bottom there, a 2 factorial on the bottom there, and we've actually calculated the exact same thing. And that's why I said both ways work just fine. But final answer would be that 525. Now, suppose you switched up on you changed up this question. Suppose instead of taking these 3 fiction books and 2 nonfiction books with you on some sort of trip where you need to hold them somewhere else, suppose instead you then decide to put all 5 of those books you selected on a shelf. Now, here's the difference between this question and the book question at the beginning of class today. You're not told that you need to separate the fiction and the nonfiction. Suppose you just throw them up there and they're all mixed together. Any guesses what we would do in that case? It turns out it's a sneaky trick. So here's the sneaky trick. You select your fiction and your nonfiction book. So 7 choose 3, 6 choose 2. I'm just going to put it in the formula form. And let me tag what we're doing. Here would be fiction. Here would be nonfiction. Now, at this point in time, order doesn't matter. You just have them like in a pile on the floor. Then, from that pile of 5 books on the floor, you put them on the shelf. So, of these pile of 5 books, what happens? You select one of them to go up on the shelf, and out of that one, you could pick. So, here's from pile of 5 books on the floor. You put them on the shelf. There's 5 books, so they'll go in 5 positions. Any of the 5 can go in the first position, then any of the 4 in the second position, remaining 3 in the third position, remaining 2 in the fourth position, and there's only one possibility in the last position. And if we actually multiply that together, that would be 5 factorial. Now, notice, with this selection, in no way, shape, or form did we care whether they were fiction or nonfiction. It was just from the pile on the floor. So this here, this one gets you the pile on the floor. So these numbers get you that pile. Then you would multiply by the total of 5 factorial, and this 5 factorial puts order back in. In other words, it takes something that's currently unordered and throws it so they now order matters. So here's the weird thing. If you currently have order mattering and you don't want it, you divide by a factorial. If you don't have order and you need to put the order back in, that's when you would multiply. And so this here would be the 525 answer that we had before times 5 factorial, and 5 factorial is 120. So that number is, what is that number? Did I write it down? This looks like it should be 63,000. So a whole lot more options when you put the order back in. And notice we didn't just multiply by 3 factorial and 2 factorial, because if we just multiplied by the 3 factorial and the 2 factorial, we get back to just the following factorials, and that would be all the fiction books would be on one side, and all the nonfiction books would also be together. So this allows the books to mix. This is the key thing there. All right, it looks like we've got enough time for one example, and this one example, I actually have it thrown to you guys, at least for the first half of it. So if you go to Pull Everywhere right now, you'll actually be able to see this exact question, which says, suppose you have a group of 5 people and you want to form a committee of 4 members from that 5 people. How many different 4-person committees could be formed from that group of 5 people? And let me throw this up here real quick in case you need to grab the URL. Okay, so that should be shared in a second screen now with you guys. So the place where you can go ahead and type in your potential answer is at polev.com/sbirdsong. So this is that same place that we've been doing for the entire course. Okay. And I'm going to go ahead and stop sharing this with you guys because it's the same question and because, well, it gets really tiny on your screen. And then we're going to have a follow-up question that we'll interpret here. Don't overthink it. You want to pick 4 people from your group of 5. And remember, in terms of committees, it's literally just picking a group of 4 people from an initial pool of 5 people. The thing, of course, that you have to ask yourself is, can you pick somebody more than once? In other words, is repetition allowed or not allowed? And does it matter in what order those people are chosen or not? All right, it looks like most of you have thrown in answers. A couple of you who haven't picked an answer yet, go ahead, pick an answer. Ooh, we've got everybody except for 1. All right, so almost everybody's picked an answer. So let us check here real quick. Ooh, awesome, and it looks like the majority of you got the right answer. So for something like this here, what do we want to do? We have a grand total of 5 people. What? Nope. We have a grand total of 5 people. We want to select 4 people. So what do you guys think? Would order matter? And are you allowed to repeat people? Well, if you actually pick 4 people from a group of 5 people, if you pick somebody twice, that's not actually picking 4 people, that's picking like 3 people. So you can't repeat people, so no would be the answer for that one. Now, does the order matter? Again, no, because all we care about is the group of people. So if order doesn't matter and repetition is not allowed, what that means is we are going to use an N choose K format. On the top is the total number of people that you're going to be using or picking from, so that would be 5. And the number of people you actually select would be 4. Now, if we wrote this out, this would be 5 times 4 times 3 times 2. Note, please, on the top, you start with a 5, and the number of factors you write out is exactly the same as the number on the bottom. Now, on the bottom of this fraction, you're always going to have 4 factorial. Now, remember what 4 factorial is. So here's our to the side. 4 factorial is 4 times 3 times 2 times 1. And you could write that out as a number. I'm going to keep it in factored form. Notice that means that this part right here, those guys all cancel, which means the answer here should have been 5. The other way that you can think of that is you picked everybody except for 1. Which one person can you not pick each time? Well, there's 5 different options for the person you didn't pick. So 2 ways of thinking about this. Now, second question, follow-up. Is it possible to have a different committee chair for each one of these possible committees? And remember the buzzword committee chair in respect to the committee, having served on way too many committees in the past, is simply the leader of the committee. So it's the one person in charge of running whatever it is that they're going to be doing. So that means we're going to need to select one of the people from each of these different committees to be the chair. Could we actually select a different committee chair, a different committee leader for each of those possible committees? What do you guys think? The only possibilities of answers there are yes or no. Ooh, I've got 1 vote for yes, 2 votes for yes. Yes, you guys are correct. The answer here is yes, and the reason for that is your total number of people, your N, is what? It is greater than or equal the number of committees that you actually picked. So this here is number of total people. Over here is the number of committees. And in our particular case, both of those numbers turned out to be 5. So we were able to select a different leader for each of the committees. Now, maybe you'd have to be a little bit strategic about it, but you could totally be done. Okay? So we are right at the point where we're about to jump into where I would have normally had us do our activity at the end of today, but we're obviously out of time. So at the beginning of Monday, we'll actually, I'll throw you guys into groups so that you can work on some of these type of questions together, and then we'll, on the latter half of Monday, we'll go and we'll wrap up some of the other details that you can see with counting, okay? But that's it for today. I'll hang out for a few minutes if you guys got any questions, but otherwise, we are done for today.